Tshung from class J1 Run. Today I will be presenting my maths project. For this maths project, I decided it would be fun if I made a square number machine. Now you may be thinking, machine? Like a time machine? Actually, it's just a fun maths machine to get to know maths square better. As you can see here, inside of the machine, there are some square numbers and its equivalent. For example, 1 square equivalent is 1, 2 square equivalent is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, and many more. Well, that is all for today. I hope you like my presentation on my maths project. Adios! Thank you!
Hi everyone, I'm Tsin from J1H. Today I'm going to talk about angle and types of triangle. In geometry, an angle can be defined as a figure formed by two rays meeting at a common endpoint. An ordinary angle can be classified into acute angle, right angle, and obtuse angle. Now, I'm going to explain the type of triangle. First one is acute angle. It's an angle between 0 degree and 90 degree. Right angle is an angle equal to 90 degree. And obtuse angle is larger than 90 degree but less than 180 degree. Next, I'm going to show you three types of triangle by angle. I am using a protractor to measure the angle. As you can see, triangle with angles smaller than 90 degree, we call it acute angle triangle. Triangle with 90 degree is right angle triangle. And triangle with more than 90 degree and less than 180 degree is obtuse angle triangle. That's all for today. I hope you enjoy learning math. Thank you.
I'm Esther from G2 Tshung, number 17, and I will be introducing a game called Deadly Red. First, we need to prepare 12 black counters, 1 red counter in the middle, and a playing board, like this. Then, a few numbers like this. This game is for 2 people, but it could be played by 3. We place the numbers randomly on the board. The player is going to first take away any numbers of the counters, but they must all be from a straight line. For example, this is player A, player B. Player A takes the numbers like this. That is on a straight line, so this belongs to A. It goes the same for player B too. And back to the first player. Player B. And the player who takes the red counter loses. That is player A.
老师您好，我的名字叫贺凯伦，我的座号是25号，我来自初2中班。今天我要介绍的游戏是 Dot and Box， 这是法国数学家爱德华·卢卡斯在1889年发明的游戏。2个玩家轮流连接横纵排布的2个相邻的点， 就像这样。画线不可以覆盖已经画好的线，不可以覆盖。每个方格最后封闭的玩家占领这个方格。每占领一个方格，该玩家就必须再画一笔。当无法再画线时，游戏结束，占领方格多的玩家获胜。这个就是黑色获胜。谢谢老师。
Today, our group would like to talk about maths is nothing without symbols, and we would also mention about some of the history of mathematical symbols. Presented to you by Cassandra, our group leader, Zoe and Yingxuan, which are our script writer, and our slide designers Nicole, Lydia, Felicia, and Xingyao. We have a total of 5 topics to discuss, and they are equations, equal, plus and minus, pi, and lastly, trigonometry. Now, let's talk about equations.
Hey Cass, have you ever wondered what was the world's oldest equation?
Now that you mention it, I'm kind of curious.
Okay, now let's have a guess. So, which one of the boxes do you think is the world's oldest equation?
1 plus 1 equals 2?
Actually, the correct answer isn't in any of the boxes, but it is somewhere on the page.
Ooh.
And here is the answer. The world's oldest equation is 14x plus 15 equals to 17. So, this equation was the first to use in Robert's Records book. Can you solve this equation? If you could, you can now tell all your friends and family that you have solved the world's oldest equation.
And the next topic we're going to share is the equal sign. And here we have this Welsh physician and mathematician Robert Record. During his time, all books were written by hand, and he wondered, how could he possibly communicate the idea of equality in his manuscript without needing to continuously writing the phrases is equal to over and over again? So, he invented, as we now all know, the equal sign. And he also introduced the pre-existing plus sign. Robert Record was busily writing a new math curriculum called the Whetstone of Wit, a textbook that introduces the equal sign and algebra into England with a systematic notation. Now it's time to talk about the 2 symbols that literally makes up our whole entire math textbook. Michael Stifel. He was the first to use the expression plus and minus. The plus and minus sign plays a big role in our daily basis. As you can see, before then, you get expressions like this one. So what's this thing? Looks difficult for us to read, right? So this is one of the zensus, the unknown we're trying to find. P for plus, 5 lots of R for radix the root, and M for minus. So it's the root of the zensus that we're trying to find. And the above expressions became something like this. And the final one, which is this.
Now, let's talk about pi. What is it? Where did it come from? And who invented it? Let me explain the formula of pi. The circumference of a circle divided by the diameter will always be the same number, no matter how big or small the circle gets. To find the circumference, we can use the formula C equals 2 pi r.
So now you all may wonder, when was pi founded? So technically, this symbol has been known for almost 4,000 years. Estimates of it appear in the works of ancient Greek, Babylonian, Chinese, and Indian.
What was the ridiculous way we used to calculate pi? Well, it's the most obvious way. Take a circle and draw a hexagon inside it, with sides of length 1. A regular hexagon can be divided into 6 equilateral triangles. So, the diameter of the circle is 2. Now, the perimeter of the hexagon is 6, and the circumference of the circle must be larger than this. So, pi must be greater than 6 over 2, which is 3. Now, draw a square around the circle. The perimeter of the square is 8, which is bigger than the circle's circumference. So, pi must be less than 8 over 2, which is 4. This shows that pi must be between 3 and 4.
And then, in 250 BC, the first calculation of n was done by Archimedes of Syracuse by using the Pythagorean theorem to find the areas of two regular polygons. Archimedes improved on the method starting by the hexagon, and then he bisects the hexagon to a decagon, a regular 12-sided shape. Then the 24th gon, 48th gon, and by the time he gets to the 96th gon, he sort of had enough. But in the end, he gets pi to between 3.1408 and 3.1429. By the year 1400, it had been calculated as far as 10 decimal places. At the turn of the 17th century, Ludwig van Coulen had calculated a 35 correct decimal places of pi. But did they finally figure out the exact value? Never. But maybe you could try and find an even closer number, if you want your brains to explode, I mean. Now moving on to trigonometry. So, what is trigonometry? Trigonometry deals with the study of angles, triangles, and trigonometric functions. Let me tell you a bit about Hipparchus. He is a mathematician and a Greek astronomer from Nika. He is also the father of trigonometry. How did trigonometry happen? Trigonometry is taken from the Greek words trigonon, meaning triangle, and the metria, meaning measure. The word literally means triangle measurement, and the term came into use in the 17th century. Last but not least, these are the methods to calculate sine, cosine, and tangent. You can use SOHCAHTOA to quickly figure out which formula to use. We have reached the end of our presentation. Thank you all for watching our video. Bye!
Our project today will be about the infinite chocolate bar trick. Before we get into the details of it, let me tell you a story. Alex and Taylor are good friends. Taylor loves chocolate. Here we see Taylor telling Alex about how he would love to have an infinite supply of chocolate to eat. Then Alex told him, what if there really was a way to get infinite chocolate?
Before we start, you will need a bar of chocolate and a kitchen knife. First, make the 4 following cuts, dividing the chocolate into 5 different pieces. Then, rearrange the pieces. Somehow, you end up with what looks like the same size of chocolate before, but this time, with an extra piece.
Taylor was amazed. He thought about all the chocolate you could have thanks to the infinite chocolate trick. But after doing the trick for a few times, a few too many times, they noticed the chocolate bar they had became smaller and smaller. Why is that?
So you're probably wondering how this rectangle got to be like this rectangle but with the cube missing. Well, let me show you. First, let's start with our original rectangle. Then let's split it up into 4 pieces. Now let's move the bottom piece to the right, and this piece to the right as well. Finally, we'll move our last piece into place. There we go. Now we have our rectangle again.
But wait a second, there's a little bit of gap there. Let's fix that. Okay, that's better. Well, actually something you may not have noticed is that this row is actually not quite as tall as this row, as you can see here. So let's move back to its original position. There we go. Now where did that cube come from? It actually came from this space right here, as I'll show you by splitting this small space back into the original cube. So 1, 2, 3, 4. And there you have it, the infinite chocolate bar.
In conclusion, the infinite chocolate bar trick isn't really infinite.
Good morning, Mr. Wong. We are Group C from Class S1 Xiao. Today, on behalf of my team, I would like to present our research for the math project on the mathematics of Rubik's Cube. The Rubik's Cube was invented in the 1900s by Hungarian engineer Erno Rubik to teach his students about the concept of three-dimensional objects. While the mechanism and structure of a Rubik's Cube is certainly deeply rooted in geometry, the craze behind the Rubik's Cube in the late 20th century offered mathematicians a window to look into a field of study through this little toy. That is group theory, the study of sets and elements within a certain structure, that is the Rubik's Cube. Since then, group theory has developed into a very complex branch of mathematics. So today, I'll be offering an answer to a question that has been posed by many people who have ever played a Rubik's Cube before. That is, how many possible permutations are there on a standard 3x3x3 Rubik's Cube, as well as cubes of some other sizes? Let's get right into it. In order to calculate how many different permutations there are on the standard 3x3x3 Rubik's Cube, we first need to understand what a Rubik's Cube is really made of, besides being made of plastic. So to achieve this, I have gladly sacrificed one of my Rubik's Cube in the name of science to accomplish this. And now I can tell you that, first of all, a Rubik's Cube has 6 center pieces, representing the 6 colors. Now these are the 6 center pieces that are held together by metal, and this is known as the core, with 6 center pieces attached to it. Now the thing about the 3x3x3 Rubik's Cube is that we have something known as a fixed center. This means that however you scramble the sides of the cube, the center orientation will still be the same because it is a 3x3x3 Rubik's Cube. And this is a good thing because we don't have to consider the center pieces during our calculations. Now, there are pieces with 2 colors on the same piece, and we call them as edges. You see, these edges have 2 colors each, and there are a total of 12 edges on a 3x3 cube. These are the edges, the ones in the middle of 2 other adjacent pieces. And these adjacent pieces, as you can notice, they have 3 colors on them, and these are known as the corners. So we have a total of 8 corners and 12 edges, and we need to include these in our calculations. Let us now proceed to some calculations. So let's take this edge as an example. How many different positions can this edge be placed in? Well, since we know that a whole cube consists of 12 edges, we know that this edge piece can be fitted into 12 different empty slots of edge pieces. Right, so this edge here, it has 12 different places where it could go to. Now what about this edge? This edge actually has only 11 possible places it can go to because one of those places has already been occupied by this edge here. And this edge only has 10 possible places it can go to. So the identity we have here, the mathematical identity for the placement of these edge pieces would be 12 factorial. Because each edge piece will have one less empty slot where it could go to than the previous edge piece. Now let's talk about the orientation of the edge pieces. we know that the edge piece has two colors. So it can either go this way or this way. For every single edge piece, it can either go two ways. So the mathematical identity we once again have would be 2 to the power of 12. Since for each of these 12 edge pieces, we can place it in two different types of orientations. So the mathematical identity we have would be 2 to the power of 12. Now let's take a look at the corners. Similarly, there are 8 corners in a single Rubik's Cube. So for any corner, it would have 8 different possible slots that it could fit into. Now this corner would have 7 because it is one of those empty slots would be occupied by the previous one. And so on and so forth. We can note the mathematical identity for the placement of the corners would be 8 factorial, because for every single corner there will be one less empty slot because it has been occupied by the previous corner pieces. Now, for the same case as the edges, each corner has 3 colors. So when we try to orientate the corners, say for example, we try to place it in such a manner that orange is at the top, or yellow is at the top, or blue is at the top, we actually find that we have 3 different types of orientation methods. So the mathematical identity we have would be 3 to the power 8, because there are 3 ways we can orientate it, and we have 8 different such pieces that we can orient it in 3 different ways. So now we have 4 different mathematical identities, which is 12 factorial, the arrangement of the edge pieces, 2 to the power 12, which is the possible ways of orientating the edge pieces, 8 factorial, which is the arrangement, placement of the corners, and 3 to the power 8, which is the total number of corner orientations. Now, the total possible permutations in a Rubik's Cube are all the products of these 4 mathematical identities. So the total possible permutations, we can just simply multiply everything together and we'll get this figure. However, this figure is wrong because we actually didn't take into account cases which are not legal, so to speak, cases which are not natural, which we cannot get from simply scrambling a cube. For example, this case, a flipped edge case we call it. It is simply not legal and it's simply not natural to get simply by just scrambling. Even if we scrambled the cube for say an infinite number of years, we will still be not able to get this type of orientation. Another example would be something like this, a corner twist, right? Anyone who has ever played the Rubik's Cube will be extremely annoyed to find his cube twisted because this is not a solvable state. So now we know that there are certain conditions in which that a cube cannot be solved, or should I say a condition in which a cube cannot even reach in the first place by natural means, that is scrambling the cube naturally. So there are a total of 12 such scenarios, which includes flipped edges, twisted corners, swapped edges, and all of these produce yet another system of scrambles. For example, a normal cube would have such amount of permutations, but a flipped edge cube would have yet another system of permutations. This makes it double the number of such permutations. Now the number of such cases which cannot occur naturally would be 12 cases. So for this number, we will have to divide by 12, and our final number will be 43 quintillion, and that's 43,252,003,274,489,856 and 000. 43 quintillion. To put that into perspective, we could cover the whole Earth's surface 27,275 times with this standard size of a cube. We can cover the whole Earth's surface 275 times over with this size of cubes with different permutations, different states of scrambled states. For example, this is a scrambled state and this is another scrambled state. And we won't be able to repeat any of those scrambled states until we fully cover the whole Earth 275 times using just these standard size cubes. And all of this in all 43 quintillion possible permutations, there is only one possible state, which is the solved state. Now let's talk about something less annoying, which is the 2x2 Rubik's Cube. It has a world record of 0.49 seconds, and it is relatively easier and less frustrating compared to the 3x3 Rubik's Cube. Fun fact, the 3x3 Rubik's Cube actually has a world record of 3.47 seconds by Du Yusheng from China. So what makes the 2x2 cube relatively easier than the 3x3 Rubik's Cube is the fact that it does not have any edge pieces. Right, the edge pieces are missing from the 2x2 Rubik's Cube. It only has corner pieces. So edge pieces, as we've discussed previously, are pieces that has 2 colors on them, and corner pieces are pieces that have 3 colors on them. So for a 2x2 Rubik's Cube, we have 8 corner pieces. And for each of these corner pieces, the way we can arrange them on the cube would be 8 factorial. Because again, the first corner can go into any of the 8 possible slots, while the second corner can only go into 7 possible slots because it's already been taken up by the previous corner. And so on and so forth, the mathematical identity we'll get is 8 factorial. However, you'll notice that on the screen it will be 8 factorial over 24. Now this is because there are certain cases which we cannot reach naturally, just like the case of the 3x3 just now. This would include the swapped corners in the 2x2 case, because there's no edges. So we have swapped corners which cannot be solved naturally, and you cannot get to it by scrambling. Right? It is not possible to get swapped edges just by scrambling. So we need to divide 8 factorial by 24, which is the number of cases that we will not get naturally, but yet it is still in the so-called arrangement. We can arrange it manually, but we cannot get it by scrambling it. So we need to divide it by 24. And the mathematical identity for the the corner placement would be 8 factorial over 24. Now let's look at the orientation. The orientation of each individual corner. Now say for example, I were to pluck out a corner, which is not really possible on a 2x2 because it only has corners. The center is a bit fragile on the inside, so I won't want to risk that. So the corner will be able to orientate itself in 3 different directions, or 3 different orientations, because it has 3 colors per corner. So the mathematical identity for this would be 3 to the power 8, since there's 8 such corner pieces which can be oriented in 3 different orientations. However, you'll notice that on the screen it would write 3 to the power of 7. Now this is because of this case. If I were to flip one corner, it will not be solvable. But if I were to flip 2 cases, it will make it an even permutation in mathematical sense, and I would be able to solve it. If I were to twist 3, if I were to twist 3 corners, I won't be able to solve it. So the thing is that if the number of the corners twisted is odd, then I will not be able to solve it, but if it is even, I will be able to solve it. So mathematically, we have to reduce the power to 3 power 7. And so the whole identity becomes 8 factorial times 3 to the power 7 over 24. And this 24 is known as the reducing factor. That means we eliminate all those possibilities that we cannot get to just by manually scrambling it. But we can get to it by manually assembling it, but that's illegal, right? Because when we solve a cube, we don't pluck it out and reassemble it. So the number of total permutations possible on a 2x2 Rubik's Cube would be 3,674,100 and 160. That's 3674160. So relatively speaking, with 3 million to 4 to the power of 4 times 10 to the power of 19, it is relatively easier. So to put that into perspective, the 2x2 Rubik's Cube can be solvable if you turn it randomly for 8 hours a day For a whole year, you'll be able to solve it 2 or 3 times. And that's roughly the possibility that you'll be able to get. Needless to say, it's still a very large amount, and that is why when learning these things, we shouldn't rely on luck and chance. We should actually learn how to solve them so that we can actually be able to solve them. Now this is the case that is solvable. Now I want to talk about something quite interesting that I've come across in my research for this maths project, which is the topic of God's number. Now if you are thinking from a religious perspective, God's number would certainly be 7, or if you're a Christian, 777, representing the Trinity and the Holy Number. However, that is not the God's number that I'm talking about. The God's number that I'm talking about is the maximum amount of moves needed to solve a 3x3 cube in any scrambled state. For example, any scrambled state, well, it has to be legal. I had one edge flipped, which is not legal. So if I scramble this up, assuming this is legal, the maximum number of moves needed to solve this cube to its original solved state would be 20. And this is calculated by computers, and it has actually been running for 35 CPU years. That's roughly 300,000 over hours of crunching through the numbers and all the possible scenarios. And we've come to a conclusion that to solve a cube to its original state, we only need a maximum of 20 moves, right? And the minimum number of needed to solve a cube would obviously be 0, since the original state itself would be solved. So the minimum number needed to solve any state of a Rubik's Cube would be 0, and the maximum number needed, and that is called the God's number, would be 20 moves. And now if you look up on YouTube of robots solving Rubik's Cubes, they'll be able to solve it very quickly and very efficiently, because what they use is the same concept, the concept of the fewest move, right? So instead of using our human traditional methods of trying to build blocks that actually match colors and try to get them to be a side of the same color as well as layers of the same color, they'll be able to identify steps or moves that will get them to align correctly to the original state in less than 20 moves, and that's God's number for a 3x3. Up to date, we have calculated the God's number for the 2x2 Rubik's Cube, which is 7. However, we have not been able to calculate the God's number for a 4x4 and other puzzle variants such as 7x7 or 5x5 or puzzles such as these. We haven't been able to do that, and in the future maybe we will, and so that's something to look out for. With that, I end my presentation with a big thank you.
The Fibonacci sequence is a series of numbers where each number is the sum of the previous 2 numbers. The numbers in the sequence have extraordinary mathematical properties and can be found in patterns throughout nature. But in this video, we are going to look inside Minecraft and see where the Fibonacci numbers appear. Here's a Minecraft chest. You can place a chest as a single block or a double block, but no matter how hard you try, you can't place a triple block. So the question is, how many ways can you place single and double chests to fill up a row of n blocks? Usually, a good way to start these problems is to start with small values of n. So if you want to just fill one block, there's one way to do it. If n equals 2, there are 2 ways, single, or just a double chest. If n equals 3, there will be 3 ways, and if n equals 4, there will be 5 ways. So if we keep on going for n equals 5, n equals 6, n equals 7, and so on, we will get this table of numbers. Take a look at the numbers in the right column. Do they look familiar? They should. They are all the Fibonacci numbers. This shows that the number of ways to fill a row of n blocks with single and double chests is a Fibonacci number. This is mind-blowing, but I would like you to pause the video now and think about why this happens.
So here is the solution. Take a look at this. Notice that the rows of chests can be partitioned into two groups. Group 1 contains rows ending in a single chest and Group 2 contains rows ending in a double chest. Now we ignore the last row of chests. Notice that these highlighted chests have the same pattern as well as this, so the number of chests for n equals 6 is equal to the sum of the number of chests when n equals 4 and n equals 5. This pattern continues for all larger values of n, and there you have it. Fibonacci numbers appears in the pattern of arranging chests in Minecraft. The Fibonacci sequence come out a lot in our nature, from how tree branches to the number of flower petals and even the shape of galaxy. See, mathematics ties closely in our life. Sometimes we should really sit back and observe the beauty of our nature. Interestingly enough, the Fibonacci sequence also ties closely to the golden ratios and computer science, but that is a story for another time.
崇正中学，
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 崇正中学56周年
56周年
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 56周年快乐！
祝福本校有更大的发展，再创辉煌。
大家好，我是黄哲贤 Desmond，1983年的毕业生，现在是在雅比从商。饮水思源，作为校友，我们深切感谢母校的栽培，但同时还是密切关注着母校的建设和发展。在这里，我愿崇正中学继续坚守伟大的办学理念，非凡的成就永远延续，继续为社会、为国家、为沙巴，甚至世界塑造更多的精英。最后，我仅代表1983年次的校友，预祝母校56周年校庆圆满成功，校务蒸蒸日上。谢谢。
祝沙巴崇正中学
56周年
56周年56周年
快乐
快乐！祝沙巴崇正中学56周年快乐！